It is great to have you with us this afternoon. I have planned a really exciting session for you this afternoon, and I need your participation, and I need for you to be listening throughout the presentation. And please ask questions. If I if there is an occasion, I will definitely address all of your concerns, all your questions uh, as they come up. And if there is any issue that I don't resolve for you by the end of this session, feel free to send me an email, and I will communicate with you. Anyway, today, as I said, it's an exciting presentation about strength of materials. What we will cover will be following exactly the topics that are identified in the NCEES documents under strength of materials or mechanics of materials. And as we go along, I will tell you that the title or the topic, the exact term that they use in their document. Anyway, let's get this started, and we will begin by the idea of stress versus strain. And all of you have seen this material on during your education in a course probably called Mechanics of Solids or Strength of Materials. And let's take a look at the concept of stress versus strain. And this is something that you're going to hear me talk about quite a bit throughout the session, and you really need to have a good understanding of these concepts. Stress. Simply, we can express stress as the force divided by the area. Remember, we use the Greek letter sigma. Sigma is what we use to designate stress. And in this particular case, we are talking about normal stress. Normal, not in the sense that it is ordinary, but it is, we call it normal because it is produced by a force that is perpendicular or normal to the area. And in a case like that, we simply take the force, in this case, let's call it P, divided by the cross-sectional area over which it's acting. All right? So that is the concept of stress. With stress goes strain, and I need for you to really pay very close attention, because a lot of people make a very common mistake when they think about strain. Whenever stress happens, it causes certain type of strain. In this case, since the stress is normal stress, sigma, it causes normal strain. And please pay attention, the equation down below. This is the equation you use to find the corresponding strain. And we use the Greek letter epsilon to represent that. So epsilon is equal to delta L over L. Now, please pay very close attention to what is in the numerator. The numerator is delta L. Delta L is simply change in length, okay? It's not length, it's change in length divided by the original length. All right? So when normal stress, let's say it's in tension, it causes extension of a member. The amount that it is extended, that would be the change in length, or delta L, and you take that divided by the original length, and that would give you strain. The common mistake is that some people, when they talk about strain, they just think it is change in length. It is not. Strain is change in length, always divided by the original length. Please make sure that you remember that. Now, a structural engineer or a materials engineer, they can look at a curve that we call stress-strain for a given material, and they can, by looking at this stress-strain curve, they can estimate the behavior of that particular material under force. And what I need for you to understand is the shape of the stress-strain curve here. This is for a typical ductile material, and there are certain points along this stress-strain curve that are important, and for the test you need to know the definitions of those points. So let's begin by the first point that I want you to understand. It is called proportional limit. All right, proportional limit. What I want you to do is be able to approximately locate and decide where along the curve this point would be, the point that's called proportional limit. And then also I want you to be able to come up with a definition. Again, they will not ask you to define it. They will give you 4 choices, and they say, well, which of these definitions would be the proportional limit. All right? Okay, so proportional limit simply is the point on the curve below which the stress and strain are proportional. In other words, all the points below the proportional limit on this curve, they are proportional. The x and y between the point 0, 0 and proportional limit, the x and y are proportional, meaning that part of the curve is linear. All right? So that's how we would define proportional limit. Let's go to the next point that's significant. And this is elastic limit. This point is called elastic limit, and the way we define this is that below the elastic limit, the material behaves elastically or in an elastic manner. However, as the stress increases, in other words, the stress is higher than the elastic limit, then the material behaves in an inelastic or plastic manner. You may ask, what does that mean that a material behaves in an elastic manner? I will tell you very quickly. Let's assume that we have some type of an object. It could be a structural element. And if we place certain amount of load on it, this force causes some type of deformation. Now, if you remove the load and the material goes back to its original shape, that is called elastic behavior. However, if you place a load on the material, it causes some deformations, let's say some change of shape, and then you remove the load, but the material does not go back to its original shape. In other words, some of the displacement remains. That is called inelastic or plastic behavior. Now, the third important point that I wanted to share with you is called yield point. Now, approximately, it is for a ductile material, the location of the yield point is approximately where this double kink occurs. And I think you could, you know what I'm talking about, the double kink in this area. All right? And that actually, yield point is where the material yields. You may ask, what does that mean when you say the material yields? In order to answer that question, I would like to go to the next slide. But before I do that, Mary, I see your question here. I will ask. I will answer that when I get a chance. And Paul has a question. Paul is asking, would you describe the difference between the elastic limit and the proportional limit? um, the proportional limit, as I said, below that point, the stress strain curve is linear. X and Y are dependent on each other. They're proportional to each other. The elastic limit is somewhat higher than the proportional limit. So they are not exact same point. However, from a practical point of view, those of you who are structural engineers or material engineers, you know from a practical point of view, it's very difficult to distinguish between the 2 points. There are a lot of cases where we take the same value as the elastic limit or the proportional limit. But I got to tell you guys, the exam you're about to take is not a practical exam. It's highly theoretical. So you need to know that there is a difference between the two. I hope that answered your concern, Paul. Now, as I told you, I want to use this slide number 7, to demonstrate to you what yield behavior is. All right? Now, here's what I want you to please imagine. Remember I told you about this double kink? Well, what if I come along and rather than showing the double kink, I approximate the behavior? We engineers, we like to approximate and simplify things. So can you imagine that we eliminate the double kink, the kink on the left and the right, and we can assume if those areas are the same, so they cancel each other out, but concentrate on that red line. It's a horizontal line. In fact, those of you who are familiar with design of steel structures, you know AISC. That stands for American Institute of Steel Construction. AISC, when they plot the stress strain curve for certain grades of steel, in fact, that's what they do. They don't show the double kink. That area of double kink, they just show the straight line like that red line that I'm showing. All right? Now, I need your help. If we have a graph, and this is a graph, it's just a relationship between the X and Y. Now, X here, please pay attention, X is strain, Y is stress. So this really just shows, this graph shows the relationship between stress and strain. Tell me, mathematically, if a portion of that curve is a horizontal line, what is that telling us about the relationship between X and Y? And if you can answer that question, then you will have a good understanding of actually what happens when a material yields. So who can tell me, what, based on what I've said, what do you think, what does it mean when the curve, the portion of the curve is just a straight line? Matthew says strain increases without additional stress. Helen says it gets longer with no load added. Yes. Mary, strain continues even when stress stays the same. Absolutely. All of these, and many of you, Arash, Ryan, Laura, you're answering questions. This is basically what happens. All right. This is what happens, guys. When the horizontal line says, look, the Y value stays the same. Think about it. That horizontal line has the same Y value no matter where you are. However, at that same Y value, X increases. So many of you, all of you actually, that answered it, you answered it correctly. So guys, this is the answer. What happens at yield is that stress remains constant. However, strain keeps on increasing. That's what we mean by yielding. In terms of force, you can think about it this way. The force stays constant, but the material keeps on deforming when it reaches yield. All right, let's move on. The next point of interest is called ultimate strength. Ultimate strength is the highest point on the stress strain curve. And then the next point that's important for you to know with the test is what we call a rupture, rupture strength. And that's where the material actually fails. All right? And then there is this idea of true rupture. There is a difference between true rupture or the other point below that we call rupture. It's also called engineering rupture. Exactly why the two are not the same and there's a difference, it's highly theoretical, and it has to do with the testing of the material, the actual testing. I'm not sure if that's important for the test. If anybody is really curious about it, let me know and I'll answer this. But I think we have more important things to cover. So let's go to slide number 11. All right, now, do you remember I said the stress strain curve is linear up to a point? I don't need for you to type it in, but can you tell me or tell yourself up to what point? What do we call that? Yes, absolutely, yes. Kevin, actually Kevin is saying proportional limit. Yeah, he's right. But anyway, and Matthew also. So up to the proportional limit, this is stress strain are proportional. Okay, so it's linear. Now, pay attention. If it's linear, then that means the slope is constant. So the slope of the stress strain curve is constant up to the proportional limit. Tell me, how do we calculate or how do we identify the slope of a line? You got it, rise over run. So rise in this case is delta y divided by delta x, rise over run. But look, y is stress, we talked about that, and x is strain. Therefore, the slope of the linear portion can be expressed as sigma over epsilon. Of course, it's delta sigma over delta epsilon, but it's y over x and it's sigma over epsilon. Now, this slope is very important quantity, and we use the capital letter E to identify it. All right? So E is the slope of the linear portion. Who can tell me what does E called? What's the name for E? Let's see. Okay, modulus of elasticity, and also some of you are saying Young's modulus. Amanda is saying Young's modulus. That's correct. Donald is just using the word elasticity. I think, Donald, I would like for you to say modulus of elasticity, all right? Not just the word elasticity. Because if elasticity is one of the choices, if you pick that one word only, even though you know the idea, you have the idea, it would be wrong. So it's absolutely, many of you are answering modulus of elasticity. And Matthew is saying just the word modulus. No, don't just use the word modulus. Modulus of elasticity or Young's modulus. All right, okay, now, let's move on. I need for you to pay attention to this equation that I have here. This is simply cross multiplication of the equation we just developed together. But take a look at it this way. Sigma is equal to E times epsilon. Sigma is stress, E, modulus of elasticity, and epsilon is, you got it, strain. That equation, that simple equation is called Hooke's law. That's called Hooke's law. Now, I want to tell you something that's very important. Many equations that we use in design of structures, whether it's steel or concrete, the design equations that we use are based on Hooke's law. They're developed based on Hooke's law. So I ask you a question. What is the limitation of Hooke's law? And what's the limitation of any equation that's developed based on Hooke's law? And Matthew is asking me, is Hooke's law only valid within the proportional limit? Absolutely, Matthew. Yes. Hooke's law is only valid within the proportional limit. And basically what Matthew is asking me is the answer to my question. Because, now, please pay attention. Since Hooke's law has this limitation, it's only valid within the proportional limit, and we should really call it within the elastic limit. Remember I told you proportional limit and elastic limit, practically we use the same value. So Hooke's law is only valid for elastic behavior. All right? And I've explained why. So, Arash, you're correct. Any equation, any design equation that's developed based on Hooke's law has a limitation, and that limitation is that it's only applicable to elastic behavior or elastic design. Let's move on. For the exam, there are certain terminology I want you to learn. All right? The first one is called modulus of resilience. Modulus of resilience, I'm depicting, or I'm showing it to you in curve A. Modulus of resilience is simply the area under the curve, the area under the stress strain curve up to the yield point. All right? That's simple as that. Modulus of resilience is equal to the area under the stress strain curve up to the yield point. Another words, or another way of explaining it, it is the amount of energy that it takes to bring a material to yield. Okay, now the next definition I want you to pay attention to is, here it says toughness, but please do me a favor. This is curve B. Add the word modulus of to it. So it should say modulus of toughness. And modulus of toughness simply is the area under the stress strain curve all the way to the point of fracture. All right? And if you think about it, this is the entire area under the stress strain curve. That we refer to as the modulus of toughness. So here it really can be expressed as the amount of energy that it takes for a material to fracture, to fail. And one other thing I will tell you, I'm not sure Amanda is saying, why are we calling it modules of toughness? In the industry, this is usually just toughness. Okay, you can call it just toughness, but let me tell you, the word, in fact, I was just getting ready to tell you that. Why is it we always, all of you are engineers, and at some point you've heard modules of elasticity, you've heard of modules of resilience, now I'm saying modules of toughness, and Young's modulus, and all of these other things that we refer to as modulus of something. Why do we say that? Where does the word modulus come from? Does anybody know that? Matthew, what you're saying is not correct. No. Matthew, pay attention to what I'm saying. Modulus of toughness, or toughness, is the area under the curve all the way to fracture, not ultimate strength, all the way to fracture. Okay. Okay, Helen says modulus is a number like an index. Well, let me tell you guys, I'm not sure, this probably will not be on the test, but I will tell you, the word modulus is a Latin word. Modulus is a Latin word which means measure, measure of. So when we say modulus of elasticity, really what we are saying is measure of elasticity. And when we say modulus of toughness, it's measure of toughness of the material. Modulus of elasticity is the measure of resilience. And sometimes people have asked me, they say, well, if that's the case, why don't we just say measure of resilience or measure of elasticity? Well, you know what? If we say it that way, any commoner will understand what we're talking about. So we have to have our engineering lingo, and as you know, we just use the word modulus. All right, very good. Let's take a look here. This is also specifically in the NCEES documents. They talk about offset method. So let me explain. It's not any difficult concept. Let me explain to you what it is. We talk about 0.2% offset. Why are we concerned about it? Well, you know, certain materials, when we develop their stress-strain curve, they do not exhibit a well-defined yield point. In other words, remember I showed you the stress-strain curve for a ductile material, for a typical steel, the one that we just looked at just a few minutes ago. When you see that double kink and you could draw the horizontal line, you know, you have a pretty good idea where the material will yield. However, certain types of materials, which we will call brittle materials, concrete is an example of that. When you draw the stress-strain curve, you don't get a well-defined yield point. So it's difficult to identify where it yields. However, structural engineers need to have a value so they can use as the yield stress in their calculations. So for materials that do not exhibit a well-defined yield stress, this is what we do. We use the 0.2% offset method. And to do it, we just simply take the stress-strain curve and literally we measure 0.2%. Don't get confused because some people say, this is 0.2% of what? Well, it's not 0.2% of anything. It is just the 0.2% point, which means you literally just measure 0.002. Did everybody get that? It's 0.002. And that we call the 0.2% offset. So on the x-axis, from the origin, you measure 0.002, you mark it, and then you draw a line. You see this dashed line? You draw a line that is parallel to the initial part of the stress-strain curve. All right? And then the location, the point where that dotted line crosses the curve, we call that the 0.2% offset. All right? Now, there is another method that sometimes you use. It is called, pay attention to the terminology. This is called extension method. And with the extension method, by definition, we measure 0.5% extension. So literally, you measure 0.005, but with this method, what you do is you just draw a line straight up, vertical. And wherever that connects with the stress-strain curve, we call that 0.5% extension yield strength. This is standardized. An engineer in Kansas City, she would come up with the same value as an engineer in Shanghai, China. All right? And Mary Hill has a question, 0.2% of what? I think I answered that, Mary. It's just the 0.002. All right? oh, Brian is saying, will those two methods give you the same yield strength? The answer is no. It would not. These are two different values. Uh, so that is why they specify you must understand which method they're using, 0.2% offset or 0.5% extension method. In reality, the 0.2%, this method I have used quite a bit. The 0.5% extension I have not used very much at all in actual work. I don't know among you, any of you have ever used the 0.5% extension or not. However, both these methods, it's not a very difficult concept, but these two methods you need to know for the test. All right, now let's make things a little more interesting, and I want you to solve a couple of problems with me. This slide, the next probably 10 or 12 slides will help us answer this question and solve this problem. But for your reference, what we are talking about is the word flexure. If you're looking at NCEES documents where they say, well, these are the topics that you need to know, they use the word flexure. Guys, what we're doing right now is dealing with that flexure. All right? Specifically, we are looking at bending stress in beams. Because a beam, when a beam is exposed to loading and a certain moment in terms of shear and moment diagrams that we reviewed together last Tuesday, well, when a beam is exposed to moment, or let's say a moment diagram, loads that cause a certain moment diagram, then the stresses that are produced in the beam are called bending stresses. In this case, they say, please compute the maximum bending stress in compression and also the maximum bending stress in tension. All right? So I need your attention because this is a very important concept and very high probability you will have something like this on the test. So let's learn it together. All right? So that's the first part of this problem. The second part of the problem, says, also please compute the shear stress at the neutral axis and also at a section 6 inches from the bottom. They're talking about the neutral axis of the cross section. The cross section, as you notice here, is a inverted T section. All right? And here we are given the loading. Let's look at what we are given. They've given us the beam. This is the beam, and they give you the location of the supports, the types of the supports, and the loads. In addition to that, they also give you the shape of the cross-section. The shape of the cross-section is an inverted T section. You can see on the right-hand side. But something else they've given you here. Please pay attention. This INA equals 97 inches to the fourth. What do you think that is? I stands for the moment of inertia. Moment of inertia of the cross-section, in this case, about the neutral axis. All right? Thank you, Amanda. And Jonathan says moment of inertia at the neutral axis. Guys, the moment of inertia concept is very important, and you need to know how to calculate the moment of inertia. In this particular problem, the moment of inertia is given to you. Pay very close attention, and if they've given you the value, just use it. Don't waste time trying to calculate it. All right? In this case, they've given it to you. In a later problem today, I will show you exactly how you would go about calculating the moment of inertia. But here, they've given this to you. All right, let's start with the first part of this this problem, and the part that I have underlined in red. finding the bending stress in compression and the bending stress in tension. All right, on slide 15, what I have shown is the shear diagram. I'm not going to go over how we constructed the shear diagram. I showed you the process last week. So what I need for you to do, please do this for me. Not right now, but later when you study these problems, don't just take my shear diagram, cover it, and do it on your own. Make sure that you know how to draw the shear diagram. Now, next slide shows the moment diagram. See down here, this is the moment diagram. All right? And once again, we will be using this moment diagram. Please accept it as the correct moment diagram, but I want you to do it on your own to make sure that you, based on what I showed you the other day, you can actually draw this on your own. And the moment diagram here, certain part of it is below the x-axis, here, negative, below the x-axis, also this part. And then certain segment of it is, specifically this part, is the beam is exposed to positive moments. All right? That is important because, and I really need your close attention here, you need to understand the effect that positive moments have on a beam. And what I need for you to do is take a look up here. You see this? You see that? That is what happens when the beam, a beam, is subjected to positive moments. All right? In other words, positive moments cause the beam to bend like this. Therefore, this would be moments that are positive would cause the beam to bend that way. And you can remember by saying positive moments are happy moments. Let me see if I can erase that. And then another way of looking at it is this. When we have a positive moments cause tension in the bottom, take a look here. This is positive moment here. And let me change the color. This is very, very important what I'm telling you right now. Positive moments cause the bottom to lengthen, to be in tension, and the top of the beam is in compression. Now, the reverse of that happens when the beam is subjected to negative moments like this. Negative moments cause the beam to flexure this way. Now tell me, which part is in tension, top or bottom? The top, because that stretches, that's in tension. All right, so write this down. Negative moments cause tension on top, compression in the bottom. Positive moments cause tension in the bottom and compression on the top. Remember this because I'm going to come back to it. To keep things in perspective, I want you to understand what it is that we are doing. We are calculating what we call the bending stress in beams. The equation is this one. This is the equation. Sometimes it's referred to as the flexure equation. Now, what I need for you to do is to understand the ingredients in that equation. Sigma is the bending stress in beams. It's equal to mc over I. Let's start from the denominator. I is the moment of inertia. So the denominator is the moment of inertia of the cross-section about its own centroidal axis. The numerator, m, is the moment, and we get that value from the moment diagram. If it is the bending stress at a specific point along the beam, you use the exact value at that specific point along the beam. Otherwise, if it's the maximum stress that you're calculating, it would be either the maximum positive moment or the maximum negative moment. The one thing I have not defined in this equation is C. So let's see if we can identify what this C value is. And this C value, guys, is the distance between the neutral axis to either the top or bottom. All right? And some of you are giving me the answer to this question. Joseph, Donald, Jonathan, Gary, they're telling me that C value is the distance between the centroid and either to the distance to the centroid from the neutral axis to the top or bottom. All right? So the question becomes, can you make up your mind? Is it the distance to the top or bottom? All right, guys, here's what we're going to do. I'm looking at slide number 16. The C value is the distance from the neutral axis to the top, or the neutral axis distance to the bottom. Now, which you use is based on whether you are measuring the stress in tension or compression. All right? So let's assume that we are, now I want everybody to do this along with me. Let's assume that we are trying to find the maximum bending stress in the region where the beam is subjected to negative moments. So in negative moments, the bottom is in tension or compression. Negative moments, the bottom will be in compression. So I think you can see this here. That we call C sub C. All right? So where the beam is subjected to negative moments, compression occurs in the bottom. So the distance between the neutral axis and the bottom, we call it C sub C. The subscript C stands for compression. Now, in the negative bottom, in the area where the beam is subjected to negative moments, but the distance from the neutral axis to the top, what do we call that? C sub T. Why? Because in negative moment region, the top is in tension. In the portion of the beam where the beam is subjected to positive moments, the reverse happens. Now, here's what I want you to do. If you have any questions, feel free to ask me, but let's take a look. I'm going to do a double evaluation. I'm going to analyze the beam for the negative moment region and also the positive moment region. I want you to go ahead and make sure you understand where these numbers come from. In the negative moment region, let me switch back. In the negative moment region, C sub T is this distance, neutral axis to the top. So what's the value of it? Who can do the subtraction? It's 9 minus 3.5. What do we get? Helen, help me out. Yeah, Matthew says 5.5. Helen, I hope that you agree with that. So C sub T in the negative moment region is the distance between the neutral axis and going to the top, which is indeed 5.5. So there it is. Let's catalog this. C sub t is 5.5 in the negative moment region, and C sub c, the distance from the neutral axis to the fiber, outer fiber that is in compression, would be 3.5. Now, move over to the right column, the reverse happens, because that is in the positive moment region. Does everybody follow this? Okay. Now, at this point, we are ready to apply the equation. So let's apply the equation. We start with the negative moment region, and sigma t. Remember, the equation, the equation is mc over I. All right. So the denominator is 97. It's 97 inches to the fourth. That was the moment of inertia. It was given in this problem. Now, here, take a look. The 6,000, where do we get the 6,000? In the negative moment region, I'm going to go back. In the negative moment region, 6,000 happens to be the maximum moment. All right? Now, in this case, this is symmetrical, so the negative moments, 6,000, are in both parts that are in negative. If it weren't, you would use the higher value. Remember, absolute value is what you go by. All right? Okay. So everybody knows where the 6,000 came from. Then, what's the unit of the 6,000? 6,000, if you look at the units, it's foot-pounds. M is foot-pounds. What about the C sub t? C sub t is 5.5 inches. So we need a conversion factor. Write it down. We need a conversion factor. Why? Because 6,000 is in foot-pounds, 5.5 is in inches, and if you look at the denominator, 97 is in inches to the fourth. So we need a conversion factor, and the conversion factor here is 12. So please make a note to yourself why we are using that 12. Then let's move on to the bending stress in compression. Again, we're still in the negative moment region. So what we have is 6,000 times 12, which is the conversion factor. Now we multiply by C sub c, which is 3.5, divided by the moment of inertia, which is given, 97. Let's move over to the positive moment region. In the positive moment region, what do we have? We have the moment which is 7,500, and tell me, that 7,500 is foot-pounds. Multiply 12, that's the conversion factor. 3.5 is C sub t now, because the curvature is in the opposite direction now. C sub c, 7,500 foot-pounds. Everybody knows where we got that. Now, this is C sub c is 5.5. All right? We get all the numbers together. Let me see if I can change this color. And here's what we're going to do. The problem asks for the maximum bending in tension. So we compare for bending in tension, we compare 4,082 and 3,247. Which one is higher? 4082. So that's the answer for bending stress in tension. That's the maximum. What about in compression? In compression, we have two values. We have 2598, and we compare that with what? 5103. So which one is the higher? This one. All right. Now, let me see if I can erase some of these things. Because I want to point out a few things to you guys before we move on to the next slide. And this is very important that you understand a few items of interest here. You may ask, or you may, on the test, you may wonder if you're given this problem, you look at the moment diagram, you say, okay, the maximum moment here is 7,500. Do you guys follow? You may say 7,500 here is the maximum moment. So I just plug that into my MC over I equation. And if you do that, guess what you get? You will come up with these sets of values. Now, you will pick up one of the correct answers, 5103. But you will miss, you will get 3247, which will be incorrect. You will miss the 4082 here. You know why that happens? Because C sub C and C sub T flip-flop when you have beams subjected to both positive and negative moments. So, do you always need to analyze, do a double analysis for these problems? The answer is no. And I'm going to tell you, I'm going to go back to the slide before, and I want to explain something to you. This is extremely important for the test. If you get a problem like this, you need to think about the following analysis. Assess it this way. Ask yourself, is the cross-section symmetrical or non-symmetrical? If the cross-section of the beam, for a problem like this, if the cross-section of the beam is symmetrical, for example, if it's a rectangle, or if it's an symmetrical I-beam, then you do not need to do double analysis. All right? However, if the cross-section that's given is non-symmetrical like this one, if it's non-symmetrical like this one, then you look at the moment diagram. If the moment diagram, the entire moment diagram is positive, or the entire moment diagram is negative, then you do not need to do double analysis. However, if you see a moment diagram that's similar to what I'm showing you, in other words, part of the beam is subjected to positive moments, some are subjected to negative moments. In addition to that, the cross-section is non-symmetrical, like this one, then definitely you need to do a double analysis like this. In other words, separately calculate the negative moment region and then the stress in the positive moment region. I hope that's clear to you. There was a question by Matthew. Matthew Wilson says, how likely is it that we get 3247 as a option on the test? I assume you're giving me the numerical value, 3247. It is very unlikely that they will give you an exact number like that. In a case like this, they would either say nearest to 3200 psi or 3240, something, and I hope that's, I answered your question. And Wesley, yes, symmetrical about both axes. Amanda, yes, you can, but it also depends on the shape of the moment diagram. All right, now, this Matthew Youngblood brings up the subject of distractors. And Matthew, you get the idea. Yes, 3247 could be, or 3240 could be in there as a distractor. But guys, let me also, before we move to the next slide, show you another distractor here. For a problem like this, they would give you the answer without the this conversion factor of 12. All right, you see that? Let me see if I can change the color. I've got too many colors here. You see this, the 12 that you and I agreed on using for all of these, the conversion factor? Well, one of the distractors that I would be certain they would use is giving you a value. I do not have it here, but they would give you a number that you would calculate without using the proper conversion factor. And that is guys, that's a very, very common distractor value. So please stay away from it. Let's move on to slide number 18. Slide number 18, um, slide number 18 shows you the concept of what we call section modulus. Those of you who are structural designers, especially if you design with steel, design steel structures, you are very familiar with this concept of section modulus. The rest of you, don't worry about design of a building. All I want you to do is please learn the concept of section modulus. Section modulus. In this case, S. The section modulus is S, and that's defined as I over C. I is the moment of inertia about the neutral axis. C is the value of C that we've been talking about, C sub C, C sub T. All right? So, by definition, section modulus is equal to I over C. And if you combine these two equations, S is equal to I over C, bending stress is MC over I. If you combine it, then sigma, bending stress, comes out to be M over S, moment divided by the section modulus. Designers of steel structures use this concept a lot to decide the dimension and what size beam to choose. In fact, I will demonstrate this to you next week. I will have an example problem. How do we use, it's not a difficult concept, but how do we use the concept of section modulus to decide the dimension of a necessary steel beam? I'll show you exactly how that's done. But for now, please remember these equations. However, on the test, morning, and also sometimes the structures in the afternoon, but we're talking about the breadth exam. They will give you a certain amount of information. They ask you what is the section modulus for this beam. For this beam that we've been talking about, the last 2 or 3 slides, the section modulus would simply be 97 divided by 5.5. Does everybody see how we got that number? You know, they'll ask you, what is the section modulus? You should be able to remember or be able to look up that section modulus is I over C. I is 97. C is, in this case, 5.5. You may ask, well, you know, there are 2 C values. One was what we call C sub C, the other one C sub T. Well, guys, use the larger of the 2. All right? Use the larger of the 2 C's, because this would be the critical section modulus. Just remember this, because this has showed up on the test before. Okay, let's move on. I'm on slide 19, and we are continuing this problem. A couple of you are asking me why 5.5, not 3.5. Well, because if you use the higher value in the denominator, that will give you the critical value. It will give you the smaller section modulus, and that would be the critical value. I hope that helps, Matthew and Chicago. All right, here we've got the same problem. This is based on flexure, topic of flexure, and we're talking about shear stress in bending. Specifically, they will say this, shear stress in bending. So as soon as you hear that terminology, remember the equation that you need is this equation. And a lot of people, for some reason, and I will explain some of the reasons that I think may be contributing to this, but a lot of people have difficulty using this equation. All right? So please pay attention and try to see if you can learn this. Remember what we're doing. We're calculating the shear stress in bending. All right? Now, the equation, as I said, is VQ over IB. By the way, shear stress, we always use the Greek letter tau, T-A-U, tau, and that's what the symbol looks like. So tau is equal to VQ over IB. I want you to understand the ingredients that go into this equation. Starting from the numerator, V. V is the shear force. So V is the shear force, and that we get from the shear diagram. All right? Q, if you don't mind, I'll get back to Q in just a minute. Denominator, I. Guys, this is the moment of inertia about the neutral axis. We've been talking about it. Then, what about B? B in the denominator, this thing is the width of the cross-section. It is the width of the cross-section. All right? Now, this concept of width of the cross-section is interesting because I'm going to go back and ask you a question here. This is slide number 19. Everybody, please, take a look at slide number 19. Let's assume that Jonathan says B is the member width. That's correct. And sometimes some books use the letter T instead of B. It doesn't matter. It's no matter what they use, it is the width. All right? But tell me, for this inverted T section, if you were, and we will do it together in just a minute, but what would you use for the value of B, the width? What do you think? Ryan, I've been calling you Ryan. I'm not sure if that's correct, but if your name is pronounced different, tell me. But Ryan says 1. John Taylor says 4. Many of you are saying 1, and Mary says 4, and John says 4. Okay, guys. Now that I have your attention, let me explain. The answer is it depends. And Arash actually is giving me the right answer. He says you decide what the width is by looking at the section in which you're doing the calculation. He's absolutely correct. So what I said was the answer, what we use as B, it depends. It depends on what? It depends on where along the cross-section you are evaluating the shear stress. And that's what Arash is saying. Take a look, guys. If, for example, you see this red line? If you're calculating the shear stress at the neutral axis, you look and see what is the width at that level, at the neutral axis. It would be 1. So if you're calculating the shear stress at the neutral axis, you use B. You take B as 1. However, what if I come along and say, please find the shear stress at a section half an inch. See if I can draw a straight line here. Half an inch from the bottom. Half an inch from the bottom. What would you use as B? Well, in that case, B happens to be 4 inches. All right? So that's exactly what you need to do, because the shear stress value changes. It varies from the top all the way to the bottom. By definition, and now what I'm about to tell you, please write it down, because this by itself could be a question. Shear stress at a free surface, either top or bottom, will be 0. All right? So shear stress in bending on a free surface, either top or bottom, will be 0. However, shear stress produced by bending has its maximum at the neutral axis. All right? All right, so the maximum shear stress occurs at the neutral axis. So if they ask you to find the maximum shear stress, automatically you have to identify where the neutral axis is, and whatever the B value, the width is at that section, that's what you use. Stephen is asking a good question. He says, what is the B value 1 inch from the bottom? And, well, that's an interesting question, because if you pay attention, 1 inch from the bottom is the interface here. I don't know if you can see that green. That's the interface. So do we use a B of 4 or B of 1? Well, I don't. This part is highly theoretical, but Stephen, you use both, actually, because at that level there are two levels of stress that act. One of them you use 4 to find it, and then you use 1. And there's an abrupt change of shear stress at that level. I don't think that level of theory is really that applicable to the exam. But Jeremiah is asking the same question. So, but that's what happens. All right. So there are two stresses at that level, and there's an abrupt change. All right. If you want to discuss that further, just send me an email. Now, let's go back to this. What about the value of Q? And remember, guys, I said earlier, um, some people have difficulty with this equation. Well, the difficulty that many people have is in calculating the value of Q, what we call Q. All right? Um, if you go to a textbook or a reference book, they define Q as the first moment of the area. First moment of the area beyond the point that you're investigating. Which is, theoretically that's correct. But what I want to do is I'd like to go to slide 21. And yeah, Donald, you're correct. Your definition is correct. What I want to do is show this to you by doing the example. All right? So everybody, please pay attention, because I know what I'm talking about. This value of Q has given a lot of people difficulty, but it's not a very difficult concept. Let's assume that we're finding the Q value. Let's say we're finding the shear stress at the neutral axis. So this is the neutral axis. The first thing that you do, you identify exactly where you're finding the stress. All right? That's step number 1. Step number 2, I want you to help me find the Q value associated with this section. This is what you do, guys. Let's take the area above that section. All right? Keep everything in perspective. We identified the section at which we are finding the shear stress. In this case, at the neutral axis. Step number 2, we are identifying the area above that point. All right, this is going to be this where I have highlighted red. Okay. Now, the next thing that I do, let's do a free body diagram of that area. And I have done that here. Do you mind moving your attention to this cross section to the left? So what I have, this is the neutral axis, cross section to the left, this free body diagram. This is the neutral axis, and the shaded blue area is that area that I just identified for you. You take that area, and then look what we do. Find the area. The area is 5.5 times 1. Does everybody follow what I got, how I got that? 5.5 times 1. 1 is the width. That's the area. Then I need to take that and multiply it by a moment arm. The moment arm in this case is 2.75. This is where things get complicated. How do we calculate the moment arm? Guys, I will tell you, and please write it down. This moment arm you need is simply the distance between the centroid of this area that we have highlighted, the distance between the centroid of the area we have highlighted, measured from the neutral axis of the entire body. So in this case, it's 2.75. Now, how do we calculate Q? We find the area, in this case 5.5 times 1 times 2.75, which is the moment area. The moment arm. What do you come up with? Well, I come up with 15.12. That is indeed the answer. That is the Q associated with finding the shear stress at the neutral axis. Please note the units, inches cubed. Inches cubed. All right, because there are 3 numbers we multiplied. Each one carries the unit of an inch. Now, let's go back to the previous slide. This is slide number 20. And I want you to please, if you don't mind, look at the bottom part of this slide. This is where we are calculating the shear stress at the neutral axis. Q is 15.12 inch cubed. I just told you exactly how we calculated that. So the equation is tau equals to VQ over IB. V is 2250. How did I get that? Go back to, I think it's slide number 19. Look at what is the maximum shear. Maximum shear in the shear diagram. You will see it's 2250 pounds. Times Q, Q is 1512. Divided by I times B. I is 97. And why am I using 1 for B? Because this is the shear stress at the neutral axis, and B happens to be 1. All right? Now, the second part of this problem says, could you please find the shear stress at a section 6 inches from the bottom? Mary is asking, is Q the absolute value? Yes, we don't need to have plus or minus signs. All right. Now, when we talk about, see if you can help me calculate this. When we talk about finding the shear stress 6 inches from the bottom, first, what did I say? The step number 1 is identify the location. All right. So it would be 6 inches from the bottom. Approximately would be there. What do we do next? Isolate the area above that section. Guys, I have done that here. So if you take a look at that, that is the area above the section at which I'm calculating the shear stress. Does everybody agree? All right. And if you look at the numbers, it comes out that way. It's 3 inches from that section to the top. Now, what I want you all to do, help me, and please go ahead and do it. I want you to calculate the Q value associated with this. Remember what we do? Simply this shaded area, find that area. It is 3 times 1. 3 is the height, 1 is the width. So 3 times 1, and then what I need to do is multiply by a moment arm. The moment arm, write it down. It's always, always, always the distance between the centroid of that shaded area measured to the neutral axis of the entire cross section. All right? So that would be 4 inches. So the proper Q here is 3 times 1 times 4. It gives you 12 inches cubed. Let me tell you a common mistake here. In fact, one of the distractors here. The distractor would be calculated. Let me see if I can erase some of this. One of the distractors, this is how they would calculate it. For Q, they would say 3 times 1, but then they would use the moment arm, not 4. 4 is correct, but what would they do is multiply by 1.5. Assuming that you will make that mistake, instead of measuring the distance from the centroid of that shaded area all the way to the neutral axis, which would give you 4, they count on you making a mistake and treating that as the moment arm. That is a very common distractor. So don't do it that way. Does everybody see the difference? Excellent. And these are the kinds of problems that I think you should spend some time making sure that you know how to do. Benjamin says, is it always area above neutral axis? Can it be below? Absolutely, yes. In fact, the Q value, and everybody, I want you to pay attention to this. The Q value, you can use the area either above or below the area at the section that you're interested in. Here, I only said above because I didn't want to confuse you. But I can get the same Q value whether I use the area above or below. Now, if you don't have a whole lot of experience with this, listening to me, you may not believe me, but you can do this later to prove to yourself. For example, here, instead of that yellow shaded area, if you use this red shaded area to find a Q, numerically you will get the same value. All right? I hope that that answers your question. Yeah, Mary, the shear would always be the absolute value we use. Joseph says, with the value Q, if you use the bottom area, yes, if you do it right, then numerically it would be the same. Guys, one of the problems that people have with the calculating Q, as I've demonstrated to you, if you understand how to do the calculation, it's not difficult. But one reason why people have so much difficulty with Q is because there is no physical meaning to the value of Q. I cannot give you a definition. All right? And a lot of people, they say, well, give me a good example. Tell me what it means. Well, I cannot, because there is no definition I can give you, but as I have demonstrated, just follow the calculations and it's not that difficult. If you have any, again, my recommendation to all of you is to please take the time to do example problems for this shear bending stress that I just covered, and previously bending stress MC over I, and also the equation BQ over IB. Do several problems like this. These are common problems that you might encounter in the morning. All right, here, this is another example for you. The vertical shear force, this is the shear force, is given to be 100 kilonewton. Here, instead of giving you a shear diagram, they tell you what the shear value is. It's 100 kilonewton. Then they say, please compute the maximum shear stress in bending. All right, what equation do we use? The equation would be, sure, the one we just covered. Shear stress in bending, VQ over IB. That is the equation that governs. All right, cool. Here's the equation. I'm on equation 24, slide 24. So shear stress is VQ over IB. If you look at what I've given you, you know the shear force, you know Q. Q you have to calculate. B, we can look at the cross-section. I did not give you the moment of inertia. All right, in this problem number 2, the moment of inertia I did not give you, and you have to calculate it. So here is where I show you how to find the moment of inertia. All right, and I will go through it. On slide 23, please pay attention in the very top. This is the general equation. It's the parallel axis theorem, but the parallel axis theorem we use to find the moment of inertia for common shapes. And this is something that you should really learn how to do. All right? So here, first you look and see the geometric shape. What does it look like? In this case, this is an I-beam, but that's a composite shape. Basically, think about it. There are 3 rectangles put together. All right, 3 rectangles put together. So we're going to look at each one separately. The very bottom I've called 1. The web is 2, and the top flange, or the top rectangle area, is 3. So let's find the moment of inertia of each one separately. I know some of you are very, very good at this, and you do not need me to explain it, but there are some among you that may have not done calculations like this for a long time. So I will take not a whole lot of time, but I will walk you through these calculations to make sure everybody knows how to do it, because as I told you, these are important types of calculations you need to know. All right, so let's start with moment of inertia of segment 1. It's the bottom flange. For a rectangle, the moment of inertia equation is BH cubed over 12. BH cubed over 12, that gives you the moment of inertia about its own centroidal axis. All right, so what we have is, in this case, moment of inertia of area 1 about its own centroidal axis. And you see that red line, let's assume that is the centroidal axis for that bottom bottom flange. All right, so BH cubed over 12. B is 120, so this is why we use 120. H is 20. And don't forget to cube it, please, divided by 12. So that is the moment of inertia about its own centroidal axis, this thing. So we take that, but remember what we're doing. We want to find the moment of inertia about this neutral axis of the entire cross-section. So using the parallel axis theorem, we have to add this AD squared. So what is A? A is simply the area of this segment we've looked at. Very simply, 120 times 20. It's a rectangle. All right? What about D? D in this equation is the distance between the centroidal axis of segment 1 measured from the neutral axis of the composite section, the entire thing. All right? So D in this case would be 90. Does everybody see where I got the 90? That's basically 100 minus 10. All right? The one thing that would be very important is please don't forget to square it. One of the distractors will be calculated by omitting that square. All right? So please don't forget to square the value of 90. That's part of the equation. Anyway, you put all of that together, you get this very large number. It's a very large number because we're talking about millimeters here. Anyway, that's the moment of inertia of area 1. Then moment of inertia of area 2. Now tell me something. As you can see, BH cubed over 12, that's the only thing I used. I did not use AD squared. Why? Okay, Amanda says because the centroid of segment 2 is exactly the same place as the neutral axis of the composite section. And that's absolutely correct. In other words, Matthew and Mary are saying D is equal to 0. You guys are absolutely correct. All right? So since for the segment 2, D is essentially 0, that's why I didn't have AD squared. And then I have to find I3. Because this section is totally symmetrical, I3 comes out to be the same as the moment of inertia for 1, but the moment of inertia total it has to be the summation of all the 3 values. All right. Please make sure that you know how to do these kinds of problems. Now, once we have the moment of inertia in slide number 24, I have demonstrated to you how we can calculate Q. I'm going to leave this up to you. Please make sure that you know how to find the Q value. That's the Q associated with the neutral axis because they want the maximum shear stress. So you must recognize the moment of maximum shear stress is at the neutral axis, and knowing that, what would you use for I? I'm sorry, what would you use for B, the width? Well, at the neutral axis, the width is 20 millimeters, and that's what I used. I used 20 millimeters for B. All right, now let's move on. This here is a problem that I have provided the complete solution for you. It is for your learning pleasure. So I will leave it to you to calculate all the stresses that's asked for, and then once you do it on your own, then please compare your results with what I have provided you. One other thing, this problem requires drawing both the shear diagram and the moment diagram. That's another thing I want you to do. Do me a favor. Without looking at the shear diagram or the moment diagram, try to do it on your own based on the principles that I shared with you this past Tuesday. All right? This is really a good, excellent homework problem for you. However, the one problem here, one thing that I haven't given you is the location of the neutral axis. You see, the cross-section is a T-section. You see it on the right-hand side. But I did not tell you, I did not give you where the location of the neutral axis is. So this is where some of you are making comments about the audio. I'm not doing anything differently. So if there is a problem, let me know. But I'm not doing anything differently with the audio. So anyway, the one thing that I want to go over is to show you how to locate the neutral axis for a simple case like this, simple cross-section. And I have demonstrated that to you here on slide 28. All right, slide 28. Some of you, hopefully many of you, are very comfortable finding this distance, locating the neutral axis. But just in case, I'm going to go over it. I will do it rather quickly because we have other things to cover, but I want to make sure. Okay, here, the first thing that I want you to do is at the very bottom, the first thing I want you to do is call that the reference axis. All right? So the very bottom axis, that red line, call that RA, or reference axis. And remember what we're doing. We're trying to find or locate the neutral axis for this section. And we don't know where the neutral axis is, so we're going to call that Y bar right here. All right, we're trying to calculate Y bar. So down here, we call that RA, or the reference axis, and we are going to measure everything from the reference axis. This is very important. Everything will be measured from the reference axis. So the equation says Y bar is equal to, well, what we need to do is divide this composite section into two sections of known shape. One is this one. We call that A1. I've called that A1. And the other one, I have called it A2. All right? Now, very quickly, the equation is very simple. The top is A1Y1 plus A2Y2 divided by A1 plus A2. Let's start with the denominator. The denominator is simple. A1 is the area number 1, in this case 0.8 times 8, and then plus A2, and that's the area number 2, which is 6 times 0.8. The numerator, however, as you can see, it is A1, which is 6.4 times a distance, and that distance called Y1. This is where things go wrong. If anything goes wrong here, that's where it goes wrong. What's Y1 equal to? Guys, please pay attention. Y1 in this case is the distance between the centroid of area 1 measured from the reference axis. Always measured from the reference axis. In this case, it's 4. Then the second part is A2 times Y2. A2 is 4.8. What about Y2? Guys, this is where you really need to pay very close attention to. Y2 is the distance between the centroid of area 2 measured from the reference axis. In this case, is 8.4. All right, good. You may say, why am I making such a big deal? This is very simple. Yes, it is indeed simple, but let me tell you where things could go wrong, and many times it does. In the heat of things, when you're on the test, you're trying to calculate this, many people, when they're trying to multiply by Y2, you know what they do? I don't know why they do it, but this is what they do. You see that yellow line here? They treat this as Y2. All right? Don't do it. Why is it not right? Because I told you, everything has to be measured from the reference axis. You cannot, in the middle of the calculations, change the location of the reference axis. Does everybody follow? Please do, because that's a very, very common mistake, and that's how they will. I will promise you, the very first distractor will be a value they get using what I just showed you. So make a note to yourself. Don't make that mistake. Stay consistent. measure everything from the reference axis throughout the calculation. Here, that's another example how to find the moment of inertia. Use this as a practice. And then, as you can see, the bending stress in tension and compression are shown to you for this problem 3 on slide number 32. Guys, how are you doing? Mary is asking, could the reference axis be chosen to be on the top instead of the bottom? Absolutely, you can do that. But if you do it, Mary, be careful. Throughout the entire calculations, just treat the reference axis as the one in the top. Yes, you can choose the reference axis to be on the top, and you will get the correct answer as long as you are consistent in doing so. All right, now, Elizabeth, I assume what you're asking is, would you see that on the test? I doubt that you will see that in the morning exam, in the breadth part of the exam. If you're taking the structural exam in the afternoon, possibly. I hope I answered your question. All right, now, there is one other topic that I have to cover for you. And this one deals with the topic that NCEES lists as combined stresses. Once again, when you look at the topics that they list, they do say combined stresses. Now, what I am about to show you next deals with that, combined stresses. In other words, what we have talked about so far, we looked at a beam that's subjected to bending. We calculate the bending stress. We looked at the shear stress in bending. And in the very, very beginning, I showed you an equation that told you how to calculate normal stress. Remember the comment I made about normal stress, sigma is equal to P over A? Well, we only looked at isolated stresses. In real situations, those of you who are structural engineers, you will agree with me. In real structures, we deal with combined stresses, situations where many of these types of stresses we have talked about occur together. Well, what I'm about to show you deals with that. So how do we resolve, for example, let's say a building. You pick a beam somewhere in the building, and you pick a tiny point somewhere on that beam. Well, given the equations so far, we can calculate specific stresses. But when we combine all these stresses on a real structure on a tiny point, how do we resolve the concept that these are different stresses acting on the same point? Well, now that you get the idea and the perspective of what it is we're talking about, let me present to you the calculations that you need. In this particular case, the method that I present to you is called Moore's circle. Moore's circle. And the best way to present it to you is through an example. All right? So I know we've been doing this for over an hour and a half now, and I know you're probably tired, but if you can give me another 20 minutes, I need your attention. So if you stay with me for another 20 minutes, I'll bring this concept to you, and then we'll be done. Actually, this is the last concept, but again, requires your attention. Let's assume that this square that I'm showing represents the state of stress. It represents the state of stress at a given point. And for demonstration purposes, we show a large square, but please understand this is a very, very tiny point on an actual beam, actual structure. All right? So when you look at the state of stress, we have these sigma x. This is, let's say, the bending stress that we calculated using MC over I equation. Or we have sigma y. This is the bending stress in the y direction. All right? What about these other stresses? I'm going to show it in, let's say, blue. This, guys, this is a shear stress. You see that? That's a shear stress. Let me tell you something about shear stresses. These shear stresses are shown acting parallel to the plane. All right? You see that? The red stresses, bending stresses, or axial stresses, they are perpendicular to the plane. The blue ones, those are shear stresses. They are parallel to the plane. The question becomes, if we know those states of stresses, then how would a structural engineer identify the stresses along this inclined plane, the dashed line or the red line? All right? So here's the problem. On the test, they give you this square. They say that's the state of stress. They give you values for sigma x. They give you a value for sigma y. They also give you a value for tau xy. Guys, these are not necessarily the largest or the maximum stresses acting on this plane, on this point on the beam. All right? So what we're doing, we're trying to see along this inclined plane, where are those maximum stresses and where are they located? One method that I told you I'll share with you is called Moore's circle. Moore's circle. Moore's circle basically is a graphical solution to this problem. This is what I'm going to show you. We need to learn how to transform that state of stress, that square on the top right, to this circle. Mary is asking, is this likely to be on the breath test? Yes. In fact, it is listed on the breath part of the test. But it's not a very difficult concept. Let's go through the problems and I'll show you. So here's what we're going to do. I'm going to show you how we go from that square to what we call Moore's circle. And keep these pages in mind because I may come back to it, page 35. And this one looks complicated. I'm not going to talk about it. When I present the material to you, then you can go back and perhaps check that out. But this is where I'm going to need your help. For the state of stress shown, please determine the principal stresses. Guys, principal stresses, that's, again, this is engineering lingo. What they're talking about are maximum stresses. So write a note to yourself. When they're asking for principal stresses, they're talking about the maximum or critical stresses. The part B says, what's the maximum in-plane shear stress? Maximum in-plane shear stress. What I'm going to do is use Moore's circle to show you how you can do this. Believe me, guys, this may look strange to you because it's been a long time you've seen something like this, but it's not that difficult of a concept. So let's do it. This is what we're going to do. Each of these faces of the square. For example, this face. You see that face that I just highlighted as red? That is going to correspond to a single point on the circle that I showed you. I repeat, that plane, red plane that I showed you, I'm going to locate one single point on the circle that corresponds to that. Now, Each point on the circle has a x-coordinate and a y-coordinate. Are you following me? Do you follow me? Each point on the circle that we're going to create, each point has an x-coordinate and a y-coordinate. All right, guys. The x-coordinate of that point is this 4 KSI. Do you see that? So, for x-coordinate of the point on the circle that corresponds to that red vertical face is 4. Now, Helen, tell me, would that be positive 4 or a negative 4? You're absolutely right. It's a positive 4. Why? Because, look at it. The stress that we show is pulling away from the face. You see the arrowhead? So, the x-coordinate is plus 4. What do you guys think the y-coordinate of the point would be? Well, the y-coordinate of the point would be equal to 6 KSI. Where did I get that? That's the shear stress. All right? So, let me see if I can write 6. Please accept that as a 6. But the question becomes, is that a plus or a minus? Positive 6 or a negative 6? Well, let's go back to 2 or 3 slides before. This is how you decide. All right? Shear plotted down or negative. If on this page, look at this. That's the face we were looking at. If on that face, the shear stress is acting upward, like it is for our problem, is that plus or minus? It says plotted down below the x-axis, so it's minus. All right? Let me tell you another way of looking at it, a quicker way. Look at each one of these separately. All right? So just look at the shear stress acting on one face. That shear stress acting on the face, does that create a clockwise or counterclockwise rotation about the center of the block? Guys, to keep things in perspective, I'm trying to decide whether this shear stress, which would be the y-coordinate of the point on the circle, is it plus or minus? This is what you do. Just take a look at that shear stress, the way it's acting, it this way upward. Would that cause the block to rotate clockwise or counterclockwise about the center of the block? Well, think about it. It would be in this direction. So that is counterclockwise. If it turns it or rotates it counterclockwise, then it's negative. All right? If it were acting downward, that would cause clockwise, it would be positive. So this is the quickest way that I can tell you how to decide that. Therefore, coming back to this problem, the coordinate would be plus 4 and minus 6. Does everybody agree? All right. Now, if you agree with that, before I go to the next slide, tell me something. Could you please tell me what are the coordinates associated with this plane right here, the horizontal plane? Well, the point would have an x-coordinate and a y-coordinate. The x-coordinate would always be the value of the normal stress. In this case, it's an 8. So it's an 8. Now tell me, would it be positive or negative? I'll wait for you. Tell me positive or negative. Negative. Steven says negative. Why? Because it's a compression. It is pushing towards the face. All right? What about the y-coordinate of that point? The y-coordinate of the point, that's the shear stress. Would that cause the block to go clockwise or counterclockwise? If you said clockwise, you're correct and would be plus 6. Does everybody follow so far? All right, now let's put this together. Remember these coordinates? This is what I'm going to do next. I'm on slide 38. Just draw the x-axis. The x-axis is going to be the sigma. Stresses are plotted on the horizontal line. Tau, shear stress, plotted on the y-axis, like that. Then the next thing is the points. You have to identify the points. 4 minus 6, I showed you how I created that. That's that point is that face. And this face here is this point here. So far, so good. So we just identified the coordinates, plot them on this xy coordinates. Now, what do we do next? Connect those 2 points. Point x and y that we created. Just connect them. Look, guys, if each of those points is a point on the circle, then this line that we have drawn from x to y, don't you agree? That is a diameter. That's one diameter of the circle. You should agree because it is correct. So what I want you to do next is just draw that line. Some people have asked me, when I cover this, they say, well, should we take tools that we can draw a perfect circle and measure? Well, no, you don't need to do that. Just be careful about approximately measuring these close to what they're supposed to be. All right. So when you draw this line, that's the a diameter of the circle. So one thing we identify is this: we need to identify the coordinate of that line, that point, the intersection of that diameter and the x-axis. And if you look at the numbers, that comes out to be -2. Please, I want you to go over the numbers. When I say the numbers, look at the 4 and the -6, the 4 here and the -8. The distance between those 2 points. Those are x-coordinates, right? So between 4 and -8, you divide it by 2, you end up at a point that has a coordinate of -2. What do we do next? Well, next thing that you do, you create the circle. And when you draw it, it does not have to be a perfect circle. Just draw the circle, approximately. All right? Now, remember, guys, what they asked us to do. They said, please find the principal stresses. Find the principal stresses. And I will show you. If any point on the circle represents a plane on this square, then as we rotate, remember, we're going to rotate different planes and see which one of these planes contains the principal stress or the maximum stress. So each of those planes that I'm rotating are presented by a point on the circle. So guys, critical thinking here. I want you to pay attention and tell me, on the circle, what point on the circle do you suspect the maximum and the minimum stress occur? In other words, what point or points on the circle will give you the highest value of x? Matthew says top and bottom. No, it's not top and bottom. Caleb says on the axis, crossing axis. Jeremy says, guys, okay, here is the answer. This one. You see this? Matthew, look at it. This point would be the point on the circle that would give you either the highest or the lowest x value, which would be the stress. Mary, do you agree with that? And the point on the left-hand side where the circle crosses the x-axis. Guys, all you have to do, now the problem, no, these are not absolute values. These carry positive and negative signs. So the problem reduces to what is the coordinate of the point on the circle that intersects with the x-axis. All right, so let's see if we can, and this is very simple. We can use the geometry of the circle to find the coordinates of what I have labeled point 1 and point 2. Next slide shows that. There it is. There it is. In fact, the answer to this question here, if you look in the bottom here, it says 6.49 KSI. KSI, that's keps per square inch. 6.49 is the coordinate of this point 1 here. And minus, Mary, look, it carries a negative. Minus 10.49 KSI is the coordinate of point 2. Now, how I did it, it's very clear here. Please take a look and follow the solution that I have here for you. But I don't want to simplify things too much. I want to step through this with you. You see this R? What do you think R stands for? You got it. That's the radius of the circle. And the radius of the circle, this is one radius right there. Let me, gosh, this is not good. Let me see if I can erase that. And here it is. This is the radius of the circle. This is the radius of the circle, and this is the hypotenuse. And you see what I did? Square root of 6 squared plus 6 squared. The 1, 6 is here. You see that? This is a 90-degree triangle. And the other 6 is this, the distance between -2 and -8. That's 6 units. So does everybody see that? That's how I calculate the radius. And then I use the radius to come up with the coordinates of sigma 1 and the coordinate of sigma 2. Does everybody see that? Now, common mistake. A common mistake is to get confused and not recognize that there are 2 points of importance here. One is the coordinate of -2. That is the center of the circle. Write a note to yourself. That is the center of the circle. The other point that's important is this. This is the origin of the axis. You see that? That's the point 0, 0. And all these dimensions are measured from the origin of the axis, from the point 0, 0. But the center of the circle also is very important because that's where the radius is radiated from. I don't know if that's the proper word to use or not, but sounds good. So does everybody see that? All right, so there it is. Those are the principal stresses. There's one other thing they asked in this question, in this problem. They say, could you also give us the maximum shear stress? The maximum shear stress, remember, that's the y coordinate. So let me ask you something. What is, yeah, Joseph, I see your question. I will answer that before we stop. What is the point on the circle that gives you the highest y value? And Matthew already answered that question. The point on the circle that has the highest y value would be this point or this point. Do you agree? It's the highest point on the circle that has the largest, the most maximum, if that's correct to say, value of the y. And y is the shear stress. All right? So here it is, guys. What's the maximum shear stress? Well, find the y value of that point, the highest point. And remember this dotted line, what is that? You got it. That's the radius. That's the radius. So there it is, radius is equal to the maximum shear stress. It's the square root of 79, and it comes out to be 8.49. 8.49. Mary, I don't follow what you're asking me. But let's go back to the comment Joseph made. Joseph says, why is the angle 2 theta? And this also, the answer I'm going to give you is the answer to Matthew's question also. Um, by definition, the angle on the circle is twice as much as the actual angle on the stress cube or stress square. I followed. I will repeat that. The angle on the stress square is always half as much as the angle that's on the circle. That's just a function of how we created the circle. All right? So that's why you see 2 theta versus 1 theta. 1 theta is the angle on the state of stress. The corresponding angle on the circle would be twice as much. I hope that answers your question. And Helen, yes, the answer to your question is correct. Is yes. All right, guys. This is all that I wanted to cover. This problem 5, I did not intend. It was not my intentions to cover this because problem 5 is not something you should worry about for the breadth part of the exam. However, those of you who plan to take the structures exam in the afternoon, I recommend that you please review problem number 5. And you can see the solution is given to you, and if you have any difficulty with it, send me an email. But if you're taking the structures in the afternoon, definitely go over problem 5. Poisson's ratio here, we will see this in a next session when I talk about, it's one of the future sessions when I talk about construction materials. We'll talk about Poisson's ratio. General state of stress, again, if you're taking the structures in the afternoon, take a look at this problem number 6. And the solution is given. If you have any further questions, let me know. These are the references I've used for this section. I hope that you enjoyed this session as much as I did. I look forward to being with you again next Tuesday. Please don't forget, 10 hours a week you must study. Have a great weekend. Stay safe. Stay warm. I'll see you next Tuesday.